We discussed the Black-Scholes option pricing model before. So today we'll simplify things and talk about the same conceptual framework, but this time, instead of talking about an infinite number of prices that can happen over several periods, let's limit it to one period and just two outcomes, either up or down, and therefore a binomial single period pricing model. So stick around, and the promise is that the binomial model for option pricing will help you understand better the option pricing model concepts already discussed using Black-Scholes, and it'll give you a deeper appreciation of option pricing per se. So consider a stock currently priced at 24, with an exercise price of 20 in one period, let's say 3 months. Now, there are only two possible prices at maturity. It will either be 30 or it will be 18. That's it. It's purely binomial. And the risk-free rate of return is 8%, and the contract matures in 3 months. To help picture this information in our head, we have this following depiction. Now remember, the option is the present value of the price differentials above K as we discussed before. Let's show then the price differential above K as follows. For the up price, the differential is 10. But notice that for the down movement, it's not above K anymore, so we put 0. By the way, in option literature, these are called the intrinsic values, so we will designate it as such to keep with option literature. The question now is this: how many call options should we short per 1 unit of stock that we already own, so that regardless of what happens at maturity, we create a fixed value, a guaranteed amount in the future, similar to creating a synthetic T-bill that we discussed before under put-call parity. By the way, we short the call because we will sell the stock that we have if the option is called. Now, let the hash symbol refer to the number of call options one must short per 1 unit of stock that we own. Therefore, what we want is to compute the number of call options, the hash number here, so that regardless if the stock goes up or down, we guarantee a fixed value at maturity. To do this, we simply equate up, which is the left-hand side, to down, the right-hand side, to force equality and solve for the hash number. So we have the equation of value given below. From our equation of value, we now solve for the hash number, which we keep in red font to be easily seen. It turns out that written this way, the hash number is stock price up minus stock price down, all over intrinsic value up minus intrinsic value down. Going back to our depiction, we write it down as follows. And visually note that the answer is going to be 12 over 10 or 1.2. This means that per 1 unit of stock that we own, we need to sell 1.2 call options or short 1.2 call options. Now, what's going to be the portfolio value, whether the stock price goes up or down? Well, let's plug in 1.2 in our equation of value, and it turns out that no matter what happens, the ending portfolio value is always 18. So with 1.2 short call options per 1 unit of stock that we own, the portfolio value is 18. So the hash number is actually some sort of hedge number, since it ensures a hedge portfolio fixed or hedged at 18 in the future. Well, so far so good. And here we are allowing for fractional units just to make the computations simpler. Now let's get the present value of our equation of value and see what happens. So we will work on both sides at the same time, like we depict below. What is the present value of the stock price now? Well, it must be 24, as the market is assumed to be pricing these two future prices in today's price, which is 24. And how about the present value of the two intrinsic values? Well, we know that these are just the price differentials over the exercise price K. So the present value of the average future intrinsic values, what we called price differentials before, must be the call premium as we discussed in our Black-Scholes option pricing model. Therefore, this reduces to 24 minus 1.2 times C, the call price, equals present value of 18. Therefore, solving for C, we get 5.287, and that's it. That's how we solve for the call price using the binomial option pricing model. Note what the hedge number is saying. It's delta stock price over delta intrinsic value, or in present value terms, it's delta stock over delta call price. So 1 over the hedge number flips numerator with denominator, and this now becomes delta call price over delta stock price, which incidentally is exactly the Greek delta, if we remember our last episode. So the hedge number we discussed using the hash symbol is actually just the inverse of the Greek delta. Now, let's rework the equation of value by using delta rather than inverse delta, meaning we'll do it all over again, but this time using delta. This simply means we flip the relationship as well. So now if we are short one call option, we look for how many stocks we need to get in order to hedge, which we now know as delta. This is accomplished by just dividing both sides by the hedge number, and we get the following equation. This time, as we will see, the hedge value is 15. Now, getting the present value of both sides as before, then the equation becomes S times delta minus the call price must be equal to the present value of 15. It turns out that regardless, the call price as computed is the same as before. So there's no change whether we use the hedge number approach or the delta approach. And the delta is also known as hedge ratio, by the way, in option literature. So for me, what's more important is you to understand the concepts and the hedge operations here, as this is key to option pricing, especially as it applies to the Black-Scholes. Now, having said that, let's now compare the binomial versus the Black-Scholes option pricing model shown here. This shows how the binomial parallels the Black-Scholes model in terms of the component parts. In fact, at the limit, the binomial should converge to the Black-Scholes, meaning, in layman's terms, is the same as the Black-Scholes if you push it to the limit. Knowing this, for the Black-Scholes model, the parallel idea of the riskless hedge using combinations of stocks and call options given the Greek delta is formally known as Delta Hedging. That is, there needs to be a number of long stock positions given one short call option, and that number is defined by the Greek delta in order to produce a riskless hedge. When this delta hedge is achieved, the position is supposedly completely hedged, and because it is supposedly guaranteed, as discussed before in our binomial example as an analog, we can use the risk-free rate of return for discounting. This was actually key in the Black-Scholes model, but it's a bit hard to see this intuition there, though it becomes evidently clear when discussed via the binomial model instead, as we have done a while ago. And this is why in times of high volatility, delta hedging becomes impossible, especially when the stocks themselves are unavailable or have prices that are extremely depressed, or when nobody wants to take positions in the option markets at all, which partly explains why the Greeks failed during the 2008 financial crisis. So there you go. This is how the binomial model simplifies the concepts that were introduced in the Black-Scholes model. How delta hedging solves the issue of why the risk-free rate of return can be used for discounting, as long as the hedge position is accomplished by a combination of long stocks and short calls, and how, at the limit, the binomial model converges to the Black-Scholes model given appropriate assumptions, especially since we're moving from a discrete model under the binomial to a continuous distribution under Black-Scholes. We hope that this proved useful to you, and if it did, kindly like and subscribe to help support the channel. That's all for now, and hope to see you next time. Ciao!